Okay, everyone. So can everybody hear me? Would you say yes? Okay, thank you very much. So we're gonna continue to, look at this DPL algorithm, especially the part where we do closed learning. Okay. So here's a quick reminder of the DPL algorithm. What this algorithm tries to achieve is that it takes the CNF formula F, and then it tries to find either satisfying assignments of the CNF formula, or you want to prove that the formula is unsatisfiable. And this algorithm is the basis of modern set solvers, which works, surprisingly well. And the overall structure of the algorithm is the one as you see in the slide. So it first initializes, so it's looking for a satisfying assignment. So the candidate satisfying assignment is denoted by A. And then in the context of Dpl algorithm, I said A is called valuation because which binding of variable appears first matters a lot. So A is regarded not as a map, but as a sequence of bindings of values to the propositional variable, okay? So initially this valuation is empty, but then the algorithm works by extending this valuation. And then mainly consists of one big part of the algorithm is step 2, which is called unit propagation. So maybe right. So step 2 is called unit propagations. And then what it does is that, it simplify the given formula F under A, and then you look for all the clauses, which is which are the conjuncts of the formula, this simplified formula F, where it only contains one literals. You look at it because this means that this literal should have value 1 in order for this formula to be satisfiable. So you look at all the unit clause and it extends the current valuation such that this literals in the unit clause will now receive value 1. Okay, so it adds value. Essentially, what it does is that it extends A so that this literal becomes true. So you keep doing this until we exhaust all the unit clauses in the formula F on the simplified formula F. Then we end up with the 3 cases. The case 3 and 4, they are the base cases. So these are, in a sense, the end of the current search. And step 5 is the case where we didn't really quite finish the search. So let's look at the step 5 first. In the case of step 5, the simplified formula is neither true or false. So these case 3 correspond to this simplified formula F. The F on the simplified F becomes true. This 4 means the simplified F becomes false. If neither of that case happens, then what we do is that we extend current evaluation by, according to some, onset strategy. This is a kind of place where designer of the Dpl algorithm bring some creativity and come up with some better strategy here. So it extends the current valuation A with extra binding for a new variable, which didn't really receive any value under A, and then you go back to step 2. Okay. Otherwise, these are the 3 and 4 case, and then in the 3 case, we found the satisfying assignment because this one is essentially saying the simplified formula is equal to true, which is satisfiable. So then we just stop and return A as a satisfying assignment. Otherwise, which means this, F simplified under A will contain false as one of the conjuncts. So it has so it contains a box means that one of the conjunct is false, which means this F simplified F is unsatisfiable. In that case, we analyze why it becomes unsatisfiable. Okay, and this analysis part is done by this learning procedure, which I'm going to talk about soon. Well, I will remind you soon. And then the learning procedure will return a clause C. And as I will explain, maybe also I explained before, one of the property this clause satisfies is that if we conjoin this clause with C, it doesn't change the meaning of F, but this extra, in a sense, redundant clause C helps search. Okay, so we do case split if the C is an empty clause, which means C is equal to false. Then we found unsatisfiability, so we stop and say unsatisfiable. Otherwise, we based on this extra C, we do backtracking and then continue search. And then this C essentially help us to avoid the same kind of mistake that we made while we are constructing this valuation A here. So valuation A, it's an unsuccessful search because we didn't really find the satisfying assignment. C help us to backtrack or undo of some of the decisions which we did while constructing A, and that essentially those decisions essentially made us fail to find the appropriate A. Okay, so this C help us to backtracking more efficiently. Now the question becomes how this learning step works, and then that's where we stopped the last time. So designing the learning algorithm is an art. I mean, there are many ways of designing a learning algorithm, and I'm presenting one particular learning algorithm. But before explaining one particular learning algorithm based on resolutions, I want to remind you of some of the things that learned clause C should satisfy. Okay, so we will describe particular learning algorithm, but most learning algorithms should satisfy the 3 bullet points that you see here. So these are these 3 bullet points that you see over here. These should be satisfied. So what's the input to the learning algorithm? The input to the learning algorithm is this state of Dpl, so the CNF formula together with the valuation, such that if it's simplified formula F under A, it contains a box. Okay, which means this formula, simplified formula, is unsatisfiable. Okay, that's the input. So that this guy is the input of the learning algorithm. Output of the learning algorithm is a clause C. Okay. Then now what this output should satisfy? This output should satisfy the 3 conditions. The condition number 1 is that this F should be equivalent to F conjoined with C. So this is based on the set representation, but for formula representation, this means that F is equivalent to F conjoined with C, which means that in terms of, when you view in terms of semantics, C doesn't add anything. I mean, C is a redundant clause, but it's useful for search. Okay, so that's the idea. The second part is that it should be a conflict clause under A, which means that this if C, so C should have a value false. Okay, so I forgot exactly which notation I use. I think I use notation like this, maybe something like this, has a value 0. Which, I mean, this notation means that the C, if I evaluate under A, has to be false. Or another notation that I used is like this. C doesn't satisfy A. Okay, A is this valuation that we have at the moment. So C is something which is not satisfied by A. Okay, so that kind of, because I mean this C doesn't, I mean because of this equivalence, this unsatisfiability here explains why A can't be a satisfying assignment, because A doesn't satisfy C, so that's why it fails. Okay, so C has to be a conflict clause. And then the last bit is also, I mean, this is something very important. C will be a clause, so C will contain, will be something like negation of a P or Q and negation of R and so on. But every propositional variable that appears in C, they have to be a decision variable in A. So this P should be a decision variable, Q also should be a decision variable, R in this case should be a decision variable. So that's the third case. Okay, another reminder about this decision and implied variable under this evaluation A. The decision variables are the ones whose values are determined by this decision step, which is step 5 in the previous slide. And then implied variables are the ones whose values are determined by unit propagation, which was step 2. So if I show you, maybe using this better. Right, so if I show you the algorithm again. So decision variables are the one which receive a value in step 5 when we make some choice. Implied variables are the ones that receive the value by this unit propagation. So what this tells us is that the third requirement to say C should be only about some of the decisions we made, not the consequences of the decisions, some of the decisions we made while we are searching for satisfying on assignment on using A. Okay, so C is only about decisions. So that's why C is useful. It tells us which decision shouldn't be made in the next time, because I mean, it kind of captures what are the reasons why our decisions involved in A doesn't lead to the satisfying assignment. Okay, now so these are 3 requirements. Semantics shouldn't change. C should be a conflict clause under A. So C shouldn't be satisfied by A. The third condition is C should only talk about decision variables in A. Okay, so these are the 3 conditions. And then now the question becomes, how should we design an algorithm that satisfies these 3 conditions? Okay. So the algorithm is defined. Okay, let me get this. So algorithm is defined like this. So it's maybe showing you all of this is better. We just look at here. So algorithm take, I said this learning algorithm, its input is CNF formula F, and then valuation A, and then output of the algorithm is learning cloud C. In this case, it's gonna be D1 in this construction. So because A is a valuation, it's a sequence of bindings of propositional variables. Okay, so A say P1 receive the value B1 as a kind of first binding that we added to A, and then P2 receive value B2 and so on. So this is a sequence. The order matters a lot here. Okay, so we look at this sequence, and then we construct our desired this target C by doing backward constructions, using backward induction. So essentially, the overall structure of this learning algorithm works like this. It first make a decisions. It pick dk plus 1, okay? And then you look at this binding pk maps to bk, and then do some analysis involving this formula f, and then based on this information, and then also look at dk plus 1. Based on that information, it constructs dk. And do the same thing for now. We look at the binding for pk minus 1, and then based on that information, it constructs dk minus 1 and so on. And although I wrote it as a P1, P2, and so on, they are not like a specific, I mean, they are determined by the algorithm, okay? So P1 can be, say, if I have a propositional variable like PQR, in some case, P1 can be P, P2 can be Q, P3 can be R. So that's a one possibility. But another case, P1 may be P, but P2 maybe R, P3 maybe Q, okay? So this order, which one comes before and which one comes next, it's all determined by how this, how this Dpl algorithm extended the valuations when we construct valuation A. Okay. Okay, so now how we do it? Now the algorithm this uses resolutions to do the construction, but so one way to understand what this algorithm do is to really think about these three requirements that I told you before. Okay. What is the next slide? Right. These are the three conditions. So the algorithm can be understood as something that tries to find the clause C that satisfies, it tries to find the clause C that satisfies these three conditions. Okay. So the first step of the algorithm is it has to start the base case, which is a dk plus 1. It pick one clause in the formula F, which is not true under A. Okay. We are in this situation, we are calling this learning algorithm because A doesn't satisfy F. So because A is not a satisfying assignment, that's why we are calling this a learning algorithm. And A doesn't satisfy F means that one of the clauses, so F will be clause 1, clause 2, and so on. So if A doesn't satisfy F, that means there are some clauses, say C2, which is not satisfied by A. Okay, if everything is set, all the clauses satisfied by A, there's F should be true under A. So that's not really the case here. So there has to be some clause which is not satisfied A. So we just pick one of those unsatisfied clause. So k plus 1 is such an unsatisfied clause, which is called conflict clause under A. So we just pick one of them. And then so that's the base case. Now let's take a step back and think about, okay, whether we are, how far we are in order to find C that satisfy these three conditions. Okay. Now look at dk plus 1. dk plus 1 definitely satisfies the first condition. Okay, why is that? That's because we just pick, one of the clause in F. So in fact, F union dk plus 1 is the same as, is exactly syntactically the same as F. Okay, so they are, because they are the same formula, they are equivalent. So the step, this part is okay for dk plus 1. But now the second part is also okay for dk plus 1 because we pick dk plus 1. That's not true under A. Okay, so that's a conflict clause. So these two are okay, but when we make this choice in the base case, but the third one is not okay. Okay, dk plus 1 may talk about some of the implied variables. Okay, so if suppose A, say P has a value 1, Q 0, R 1. Then suppose that these two guys are decision variables, and then this is implied variable, but maybe dk plus 1 might be something like Q or not P. Okay, so it maybe talk about some of this implied variable like a Q here. Okay, so the third condition is not true. So in a sense, what the algorithm tried to do is try to change dk so that the third condition becomes true. And that's how the algorithm works. So now it does this by looking at all these variables one by one. So at each inductive construction, so we have constructed the up to I plus 1. So initially, I is equal to k, so this is equal to dk plus 1 initially. But then we are constructing from here dk minus 1 and so on. Okay. Now, when we are we constructed up to dk I plus 1, we look at the current propositional variable, the propositional variable pi. Okay, so that's in the case of dk plus 1, pi is going to be pk. Now, if pk doesn't appear in di plus 1, or it's a decision variable, so it's a so this assignment is a decision assignment in A is a decision assignment, then as far as this third condition is concerned, pi doesn't cause any problem at all. Pi doesn't appear in C, so it's not causing any issue at all. Or if pi appears in C, it's a decision variable, so it doesn't cause any problem at all. So we just skip pi in that case. Okay. So from di plus 1, we set di is equal to di plus 1. So we make a progress. Beforehand, pi potentially cause an issue in di plus 1, but in the case number 2, we realize it doesn't cause any issue. It's because it's either decision variable already, or it's not mentioned in di plus 1 at all. So we just set di is equal to di plus 1. So that's just easy case. Difficult case is that pi does appear in di plus 1, but it's not a decision variable. It's an implied assignment, or implied variables in A, in variation A. Furthermore, we have some information that, implied variables are the ones who receive the value in the unit propagation, step 2 in the Dpl algorithm. And then we have an annotation that said pi received value bi because of the unit clause. But then that unit clause really come from this CI in the original formula F. Okay. The CI is a clause in F, which when you simplify during this Dpl algorithm, it became a unit clause. And then that unit clause forces us to set pi to bi. So that's the kind of information that we record there. So this is a bit more problematic case. pi is an implied assignment. It's not a decision assignment. And then pi does appear in di plus 1. So we have to do something about it. We have to get rid of pi. So now how to get rid of it? And then we do it by resolution. Okay. Let's look at try to consider why, so what does the CI actually look like? Because on the simplification, so suppose that we consider, to understand this algorithm, we consider simple case, bi is equal to 1. Okay, bi is equal to 0 case, it looks very, very similar. In this case, we know that CI, we don't know all about CI, but we know that CI have a bunch of literals, L1, L2, and so on, Lk, and which only mention variable p1 up to pi minus 1. Because when it simplified it, all of this disappeared. And then furthermore, the last part, when we simplify this, we end up with a unit clause that force pi to have a value 1, which means that the remaining part should have a pi. Okay. So when we simplify the formula F under A during the algorithms, all these literals here, they all become false. So they all disappear from this clause, and then only pi remains. So that's why we end up with a unit clause, and then that's why we have this implied assignment in our evaluation A. Okay. So I'm just telling you, okay, if we have implied assignments and then the bi is equal to 1, CI should have this form, which is it has a L1 up to Lk, which are all about propositional variable p1 up to pi minus 1. And then the last part should be equal to pi. That's because, this unit, this binding said pi should have a value 1. Now for di plus 1, we said di plus 1 contains pi. So it contains either pi or negation of pi as a clause. as a literals, but it can't really contain this pi. That's because di plus 1 is a conflict clause. It's a clause which will have a value false under A, but A binds pi to have a value 1 here. Okay, so because of this, pi has a value 1 under A. So if di plus 1 is not, so if di plus 1 is not satisfied under A, this case cannot really happen. Okay, so it should be the bottom case. So it should contain pi in the negated form. So now we are in a situation where we can apply the resolutions. Resolution can be applied when we have one clause that contains some literals, another clause that contains its complementary literals. So if we apply the resolutions, the reservant will be, which have a L1 up to Lk. So these are the part from Ci together with this remaining part. So this remaining part will go to the rest of the reservant. And then you can see that, in doing so, we get rid of a pi from the clauses that we are constructing. Okay, so that's how the algorithm works. It starts from dk plus 1, which is one conflict clause inside the formula f under A, and then it do the backward induction starting from the pk. And then if it's a decision, it doesn't cause any issues with the third property we care about, which is the P. This binding is either decisions, assignments, or not mentioned in di plus 1, which just doesn't do anything. Otherwise, we use resolution to get rid of a pi. So that's how the algorithm works. Now, I think the best way to run this algorithm, there is no mess. So to actually run this algorithm, so here's the theorem which said if we run this algorithm all the way until D1, we end up with a clause that satisfies the three property that's mentioned that's the kind of property that we want to get. Okay, these three property we talked about. Now, what I want you to do now is to actually run this algorithm to a specific case, and then also think about how to prove this proposition. So I will give you maybe 10 minutes to think about the first run this algorithm for solve exercise 1, another maybe 5 or 6 minutes. So it's a total 10 minutes. So spend about 5 minutes and so on to run this algorithm for specific example that I will show you soon. And then second, try to prove this proposition. Okay. So the specific example is this one. Right. Okay. So this is a specific example. And then in these examples, we start with A, and then the formula is a conjunction of C1 up to C5. If we do unit propagations, what's the exercise in the last lecture? If we do the unit propagations, then, sorry, I think maybe just was the next slide. Right. If we do the unit propagation, we end up with setting the values to all the variables. So P5 becomes 1, 6 becomes, sorry, 6 becomes 1, 7 becomes 1. They are all implied assignments. And then in that case, we reach the conflict because C4 is being false under this extension. So in this case, A is going to be, A prime is going to be the same as A in this A here, together with, I'm gonna just write it like this, P5 is 1, so implied clause P6 is 1, implied clause P7 is 1. Again, this is implied clause. And regard the first 4 as the implied assignment, say the first 4 as a decision assignment. Okay, so apply these algorithms in this example and compute compute the clause to be returned by this algorithm. Yeah, I will give you 5 minutes to do this. So let's solve the exercise 1 first. Okay, so let me, it's not quite 5 minutes, but let me just show you how this works. Okay, so let's look at how this algorithm works. So algorithm is given, the input of the algorithm is this F together with A prime, which is consisting of this A with this extra guys. Okay, and then the first step of the algorithm is this guy. And try to pick up, dk plus 1, in this case, d of 8. D of 8 will be set to some clause inside F, which is not satisfied. Okay, and then we said in the answer of this question that C4 is not going to be satisfied on the this assignment. She's call it A prime. So that C4, if you look at this, then that's this guy, which is not P1 or not P7 or not P5. Okay. Then you can see that this, this is D8. We have a 3 conditions or requirements to meet in order to produce the appropriate Lond clause. The first was preserving doesn't change the meaning. So it doesn't change the meaning. Also, it's a conflict, should be conflict clause. And the third, it should only mention decision variable. But for the third case, it doesn't satisfy this because of this is P7 and P5. Okay, so these are the problematic case. So now look at this backward induction. Now we have to construct these 7. So to do so, we look at the last assignment under A prime, which is P7 becomes 1. And then this is an implied assignment, as you can see this annotation C3. Also, this exercise said constructing this assignment using unit propagation. So we look at where, what clause made us to have this P7 have a value 1, which was C3. Okay, so we look at C3. And then P7 appears in the 8, and it's an implied assignment, implied variable. So we do the resolution to get rid of P7 there. So if you apply the resolution over C3 and then D8, P7 disappears, negation form and the positive form. And then what we get afterwards is going to be negation of a P1 or negation of a P5, or because negation of P1 appears again, so we don't have to write it and have a negation of P6. Okay. Now, we look at the P6. So next one is a P6. P6 appears in this 7. It's an implied assignment, so you also have to apply the resolution to get rid of it. And then this implied assignment to say this binding is actually coming from clause C2. So we look at the clause C2. And then we look at P6. If we apply the resolution there, then resolution will get rid of this P6 positive and negative. And then we end up with D6, which will contain negation of P1, negation of P5, and that's it. It happens that C2 is exactly without P6, so negation of P1 or negation of P5. So that's what we get there. Now we look at the next one, which is P5 as a value 1. It's an implied assignment again, that P5 also appears in this 6. So, and then furthermore, we said this implied assignment is coming from C1. So we apply the resolution on C1 and D6. In this case, the resolution, the proof of the resolution will get rid of P5. And after applying the resolution, what we get is D5 which is equal to negation of P1 or negation of P4. Now, after this, all of P1, P2, P3, P4 are decision variables. Okay, so it hits this is the second case of this algorithm. So it doesn't really change anything, so that D5 becomes D4, it becomes D3, and so on, so that eventually it becomes D1. So that's the output that we return. But what this tells us is if, this is a either P1, well, at least one of P1 and P4 has to be false. That's what this is telling us. If we take its negated version, it means that if we set P1 and P4 to 1, we are doomed to fail. We will never be able to find the satisfying assignments. So that's what this learned clause tells us about the formula. And so what this this identify the reason for not being able to find satisfying assignment under A. The reason was, if we put combination of these two, we will always will fail. And so the next time when it backtrack and try something new, it will try different version where P4 is now bound to 0. Okay, by the Dpl algorithm. But anyhow, so the algorithm runs this way. Okay. So now the next question is how to prove this theorem. So I will give you maybe 2 minutes to think about how to prove this theorem, this proposition in the slide that you see on the screen. And then maybe show you the. So that means the output of this algorithm will satisfy all these three. Okay, let me show you the proof. I need a bit of space, so I will move things around a little bit. Okay, maybe just put it here. Also put this one over here. Right. So how we can prove this? So we can prove the correctness of this algorithm. In other words, the learned clause satisfy all these three requirements by doing inductions, or you can view it as invariant-based arguments. So what we'll show is that the proof sketch. So what we will show is we will show that each of this GJ constructed by the algorithms will satisfies the following three property. The first property is that it doesn't change the meaning of f, dj. So it's very much like the three conditions we talked about. The second property is A doesn't satisfy dj. That is, dj is a conflict clause. And then the third is all implied variables in dj are included in P1 up to Pi minus 1. What does that mean? That means we are saying it doesn't really satisfy the third conditions that we have to meet, which is every variable appearing in dj has to be decision variable. None of them should be implied variable. We are not really meeting that requirement yet, but we are quite close as we make progress from dj to dj minus 1. So the third property say all the implied variables, problematic variables, are in a sense limited. They're all restricted up to d1 up to p1 up to pi minus 1. And so this is the property that we prove by induction. Okay. So every dj satisfy these three conditions, we prove it by inductions. And then base case is easy because base case, it's a backward induction. In this case, base case is, in our case, is dk plus 1. And as I said, this case is easy. We already talked about 1 and 2 are okay. That's what I told you multiple times before. But for 3, we are okay because this P1 up to Pk is essentially the domain of, this includes every variable. It's a domain of A. It includes all the variables. So it doesn't cause any issues at all. So this condition 3 doesn't say anything in this base case. Now for inductive case, so we have two things that can happen. Either we have a step 2, where dj same as dj plus 1, or step 3, where in the dj is a resolution of some c and dj plus 1, where pj is eliminated. Okay. All right. So in this case, again, we don't have anything to prove. Among the three conditions we have to meet, semantics doesn't change, and the conflict clause, we didn't change anything about DJ from DJ plus 1, so both of them are still true. By induction hypothesis say DJ plus 1 satisfies all three, from which we can deduce DJ satisfies 1 and 2. For 3 is also true because, I mean, the only problematic case in this case is a PJ. It is an implied bar. No, it's a decision bar. You can do it using DJ. I mean, if we do induction, you can think of it's a Juyeon ask whether we should do DJ minus 1 and DJ. You can do it this way, or you can think about DJ and DJ plus 1. So we are saying induction hypothesis is true, holds for J plus 1. So that's and sorry, let me double check. Okay, yeah, so it's true. And therefore, in this, when we constructed the DJ, let me, yeah, so when it comes, so this is okay. I think this is okay because when we construct DI, we get rid of PI. So if you look at property 3, we get rid of propositional variable PI. Yeah, so I will tell you, okay, for what I meant. So we get rid of propositional variable PI, and then you're right, sorry. This one has to be DJ. Oh, thank you very much. Let's get rid of this. Yeah, so yes, so please say something. I mean, this is not very easy to kind of interact with you. So if you get lost, please say something, but anything to me. And okay. Right, so then step 2, we know that Pj is a decision variable, or is a decision bar, or Pj doesn't appear in dj plus 1. She is equal to dj. Okay, so what does that mean? This means that, I mean, when we move from dj plus 1 to dj, as far as this third property is concerned, the only things that can cause an issue is pj. Okay, up to pj plus 1, no, because I mean dj plus 1 ensures everything is okay up to pj minus 1, but when you reduce the index by 1, pj can potentially cause a problem. But step 2, this condition of the step to say, actually that's not the case. pj is decision variable, so then it's not going to be included in when we compute this property 3 will be true, or PJ doesn't really appear in the DJ plus 1, so it's not going to cause an issue with the 3 either. Okay, so these are the step 2 is the case where, I mean, the induction hypothesis is exactly what we need to say that this DJ satisfies these 3 properties. It's some simple case. Now the more difficult case is step 3. Okay, for step 3, okay, Step 3, this dj is obtained from C and dj plus 1, and C is something inside the formula F. Okay, and so what we know is C is in formula F, and F is equivalent to F union dj plus 1. So by the resolution lemma, which say that if we apply the resolution, we get something implied. Okay, we will never get, we will always get something weaker. So resolution lemma, we know that C and dj plus 1 implies dj. Okay, so this is what we get from the resolution lemma. And C is inside the F, dj plus 1 is inside the F. So this means F implies, I mean, that the adding dj plus 1 doesn't change the meaning of F. So that means F implies dj. And that ensures we have F and F union dj are equivalent. Okay. So because of this, we have this equivalence here. So that means the requirement 1 is okay. Now requirement 2 said it has to be a complete clause. So that what does that mean? That means we have to show that ensure A doesn't satisfy the dj. Okay, so this is a requirement 2, and now the question is why this is the case. And this is because of the some of the properties that we can assume. So by induction hypothesis, and so, and then furthermore, we know that if C, this clause C that we are talking about should have, because of this, we are talking about implied assignment. C should have the form L1, okay, and it has, let's consider the one case. So we will consider where A of Pj is equal to 1. Okay, so if the C will have this form, but okay, so this, but then because we have a unit propagation, which means that these guys will contain propositional variable P up to P j minus 1, and then they will all become false under A. That's why unit propagation, when we simplify the formula, we are forced to set Pj to 1. Okay. Unit propagation on C, which means that under A is all of Lj, they are all false, j up to 1. Okay, okay, so where we are in a setting where for C, except Pj, all the literals are false. Also, A doesn't satisfy dj plus 1, okay, which is dj plus 1. If you look at this one will also look like L1 prime, Ln prime. And then in our case, instead of Pj, it will have negation of Pj. But because A doesn't satisfy dj plus 1, A is not going to satisfy this guy, also this guy, and this. None of this will be true under A. Now what this dj now look like? dj is defined by L1 up to Lk, and then L1 prime up to Lm prime. But what we know is, so then A, since A doesn't satisfy Lj, and also A doesn't satisfy L prime, maybe L for K and 1 through M. Another A doesn't satisfy DJ. So because A doesn't satisfy any of the litters, A doesn't satisfy these litters because C kind of induce a unique clause under A. This doesn't satisfy any of these guys because by induction hypothesis, A doesn't satisfy DJ plus 1. And then all these primes guys are coming from DJ J plus 1. So with both, if you combine these two facts together, A doesn't satisfy the DJ. Okay, so this gives, say, the requirement 2 are okay. Now for the requirement 3, so for requirement 3, and if we now go back and think about what we have so far, we said the DJ should, we said, look like this guy. And then for in the inside there, in this L part is of this form that they only contain P1 up to Pj minus 1. Okay, so L1 up to Lk will never cause an issue with the third property. The third property said all the implied variables should be included from P1 up to Pj minus 1. So, I mean, if the variables are in this set, it's not an issue at all. Okay, this condition doesn't say anything. Now, for the other part, we have to look at, so the other part is this guy, and they are coming from here, which is DJ plus 1. So it's by induction hypothesis, we know that all the problematic variables, all the implied variables in DJ plus 1 are included in a set from P1 up to Pj. And then we isolated part which contains Pj here. So this part will, all the implied variables here, they will be included by in a set P1 up to Pj minus 1. The only exceptional part is isolated here. So if you put these two factors together, primed part not cause a problem because the implied variables are included from P1 up to Pj minus 1. Non-primed part not cause a problem because of this, they are included in P1 up to Pj minus 1 because of the unit propagation property. So these two factors together say that this requirement 3 also holds. So this can be conclude a proof. Yeah, I know that in some sense I'm very detailed, and in some sense I'm not very entirely thorough if you view this as a mathematical proof. But I hope you get the idea. The key idea of the proof is to show that the algorithms ensures that the property 1 to 3 are true, and this can be understood as an invariant property or some property which is accomplished when we apply this backward induction in the algorithm. Okay, and then we can prove this property is true for the base case. Also for inductive case, you can prove this property. And doing the proof of handle the inductive case, just like any other inductive proof, you have to use induction hypothesis. At the same time, you have to use two key things. One is properties of the resolution, which is a resolution lemma. The second one is properties about the unit propagation. Okay, So unit propagation, resolution, induction hypothesis. Let us handle inductive case. Okay. I hope I didn't confuse all of you. I know it's C can contain PK, but they will be all decision variables. So sorry. For C, okay, let me just show you. So Songuk asked me this following question, which is that if you look at this C, I said, so let me just show you. So if you look at this C, I said the C only contains propositional variable P1 up to Pj. She implicitly say it doesn't contain any propositional variable Pj plus 1, Pj plus 2, and so on. So then he's asking why that is the case. Okay, the answer is that that's because we have because Pj is an implied variable. Okay, so why that what I just said is an answer. Let me just show you. So this one is why not pk for some, not case. So pl for some larger than j. So why this part doesn't contain this? That's because this pj, this binding that pj should have a value 1 is added by unit propagation. Okay, so as I said, when we look at the algorithm of DPLL, DPLL algorithm will gradually construct A. Okay, so Dpl algorithm will gradually build A, and when it apply the unit propagation on, and then when it realize Pj should be bound to 1 on the unit propagation. Now let's just take a step back and think about what A looked like at that point. A, in that case, will contains the binding for P1 up to Pj minus 1 at the time, but not anything further. Because it's a valuation, it will gradually add new bindings for the propositional variables. So when you decide to add this extra binding, Pj becomes 1 on the unit propagation. That means at that time, when you simplify the formula at that time, the A will look like it's going to be a binding. It provides a binding only for P1 up to Pj minus 1, nothing else. Okay, so that's why so PA looks like it's a bind. It provides a binding only for P1 up to Pj minus 1. If clause C becomes a unique clause under that binding, okay, that means all the literals except Pj should only talk about P1 up to Pj minus 1. For instance, if we talk about, suppose if it contains, say, Pj plus 1, disjunction like this, then C will not be a unique clause under, under this setting. So because this A at that point is not going to provide any binding for Pj plus 1. So this is very important. Whenever we apply the unit propagation in step 2 of DPL algorithms, all the variables that get a value in the unit propagations, the remaining literals in the clause will only mention previous variables, not anything in the future. Okay, so this is a specific property of the unit propagation in the algorithm. So that's why this one doesn't really talk about PL. It's a long answer. I hope you get some idea. Any other questions so far? Okay, so then I will go back. So this is a specific, the example, the execution of the learning algorithm that I discussed before. Then actually this slide set is over. So my friends, James included an examples of a formula. So in this examples, we encode this fork-in problem, which is so we can skip this last example, okay? Because it just say if you apply the DPLL for this particular problem, formulas become simplified dramatically and you get the answer very quickly. So I think more important bit is maybe I just answer questions from students. So for step 3, let's see. That's right. I mean, this is the subscript for C is just nothing. I mean, this just means that it's a clause. It doesn't have to be the ith clause in formula F. It just means some clause which forces us to have bind PI to BI using unit propagation. It just say where this unit propagation really happens. And so this is sub index C, this subscript I doesn't mean anything. So any other questions? So if you are confused about this subscript, you don't have to worry about this. Original F, C, and D. I'm a bit confused about what you mean by, so Jangon asked in the original implementation, we should take care of original F, C, and D. So you meant by the given F, so F can be extended gradually, and right. So for C, we should record for so original F. You don't have to worry about original F. I mean, it's a step of the algorithms. So the F get extended only when we do learning. Okay, so in the searching phase, which is step 2, 3, 5, okay, not 4, the 2, 3, 5, formula F remains fixed, and after only the learning, F become changed. And then we don't need to really keep the original F. So this C is really from the current F, okay? Okay, the C here is with respect to the current F, not necessarily the input F. Okay, that's one thing. And then so for and we don't need to remember that, I mean, all these we don't need to remember which one is really input, which one is not input. It just F get extended, and throughout the algorithm, this is extra. I mean, this is CI is really like a pointer which say what clause in the current F makes PI to have a value BI on the unit propagation. And then D will be returned by this learning algorithm, and that will be incorporated into F. Then you can forget about, I mean, this D. Now D became a part of F, and then the next iterations, D is not something special. So any other questions? So just to say again to Changgon's question, we don't really need to distinguish which one is really input, which one is something we added later. It's all with respect to the current F. Yeah, so that's how the algorithm works. Okay, so then let me finish these slides and then so give you quick conclusions about. Okay, so just to sum up about what we did so far, we talk about resolutions, and then also which is a very simple proof calculus for showing unsatisfiability, essentially. And then we use the resolution proof system to design variable elimination algorithm by, I described the variable elimination algorithm based on resolution, which is invented by Davis and Putnam. And then Dpl algorithm is another algorithm that uses resolutions. And then it does, in particular, we talk about this cross-learning part. And this DPLR is the basis of modern set solvers. And then you will have to implement this DPLR algorithm for your project. Okay, so that's it for today. And I will be here for about 5 more minutes. So if you have any questions, feel free to ask me. So next time we're going to talk about compactness theorem.